In the vast expanse of our solar system, Jupiter reigns supreme as the largest planet, a colossal gas giant whose presence has profoundly shaped the cosmic landscape around it. This awe-inspiring planetary titan is not just notable for its immense size, over twice the mass of all the other planets combined, but also for its role as a cosmic guardian, protecting the inner solar system from potential impacts and providing a stunning array of natural phenomena that captivate both scientists and enthusiasts alike. As we embark on a journey to unravel the mysteries of Jupiter, we will explore its composition, atmosphere, magnetic properties, moons, and its significant influence on the solar system's evolution. At first glance, Jupiter's most striking feature is its sheer size. To grasp the magnitude of Jupiter's scale, imagine the entire mass of the other 7 planets in our solar system combined. Jupiter outweighs them all. This gas giant, composed primarily of hydrogen and helium, shares a fundamental similarity with our Sun, which is also predominantly made of these 2 lightest elements. However, don't be fooled by its gaseous nature. Beneath Jupiter's thick, swirling clouds lies a complex and enigmatic internal structure. Unlike Earth, which has a solid surface, Jupiter is a massive sphere enveloped in a dense atmosphere. Its atmosphere is predominantly hydrogen, about 90%, and helium, approximately 10%, mirroring the composition of the Sun. Yet, what seems like a massive balloon of gas is far more intricate. Deep within Jupiter, the pressure is so intense, over 3 million times greater than that on Earth's surface, that hydrogen undergoes a dramatic transformation. Under these extreme conditions, hydrogen behaves as a metal, conducting electricity and contributing to the planet's powerful magnetic field. At Jupiter's core, scientists speculate there might be a dense mix of heavier elements, but the exact nature of this core remains one of the planet's greatest mysteries. Some theories suggest a solid core surrounded by liquid metallic hydrogen, while others propose that the core could be partially dissolved into the surrounding layers. Jupiter's massive size and gravitational influence have significant consequences beyond its atmospheric composition. The planet's immense gravitational pressure causes it to emit more heat than it receives from the Sun. This phenomenon is a result of 2 factors: the ongoing process of gravitational contraction, where Jupiter's immense mass slowly contracts under its own gravity, and the residual heat from its formation over 4.5 billion years ago. This internal heat plays a crucial role in shaping the planet's dynamic and complex atmosphere, contributing to its striking visual features and climatic patterns. One of the most iconic aspects of Jupiter is its atmosphere, renowned for its swirling cloud bands and powerful storms. These bands, composed of ammonia clouds, give Jupiter its distinctive striped appearance. The atmosphere is divided into lighter-colored zones and darker belts. The zones are regions where gas rises and forms towering clouds, while the belts are areas where gas sinks, revealing darker material beneath. These bands circle the planet in opposite directions due to differential rotation, creating powerful jet streams that fuel intense storm systems. Among the most famous of Jupiter's storms is the Great Red Spot, a colossal anticyclonic storm that has been raging for at least 350 years, possibly much longer. This storm is so enormous that it could comfortably contain Earth within its bounds, about 1.3 times the diameter of our planet. The Great Red Spot is a high-pressure system with wind speeds reaching up to 432 kilometers per hour, 268 miles per hour, making it one of the most powerful storms in the solar system. It offers a window into Jupiter's atmospheric dynamics, but recent observations from the Hubble Space Telescope and other missions have shown that the storm is shrinking. Since the 19th century, the Great Red Spot has diminished in size by more than 50%. Whether this shrinking signifies the storm's eventual dissipation or is merely a phase in its long life cycle remains uncertain. Some researchers speculate that Jupiter's lack of a solid surface allows the storm to persist and maintain its intensity, unlike hurricanes on Earth that weaken upon making landfall. Jupiter's magnetic field is another remarkable feature. It is the strongest of any planet in the solar system, extending up to 3 million kilometers, 1.9 million miles, from the planet, reaching beyond Saturn's orbit. The strength of Jupiter's magnetic field is about 20,000 times stronger than Earth's, generated by the planet's rapidly rotating metallic hydrogen core. This immense magnetic field creates a vast protective bubble around the planet known as the magnetosphere. Within this magnetosphere, high-energy particles from the solar wind are trapped, forming a radiation belt far more intense than Earth's Van Allen belts. The radiation around Jupiter is so intense that it poses a significant hazard to unshielded spacecraft electronics and future human missions. Understanding this radiation environment is crucial for the design and operation of space missions, such as NASA's Juno mission, which must navigate through Jupiter's intense radiation belts to collect data. Despite these challenges, Jupiter's magnetic field also produces stunning auroras at its poles. These auroras, much more powerful than Earth's northern and southern lights, are caused by charged particles from the solar wind interacting with Jupiter's atmosphere. Interestingly, Jupiter's auroras are also influenced by material from its volcanic moon Io, which continuously spews sulfur and oxygen ions into the planet's magnetosphere. Jupiter's system of moons is as captivating as the planet itself, with 95 known moons and more being discovered regularly. Among these moons, the Galilean moons, Io, Europa, Ganymede, and Callisto, stand out due to their unique characteristics and the insights they provide into planetary science. Io is the most geologically active moon in the solar system, with over 400 active volcanoes. These volcanoes continuously erupt, spewing sulfur and sulfur dioxide across the moon's surface, creating a vibrant and colorful landscape. The intense volcanic activity on Io is driven by tidal forces exerted by Jupiter and the gravitational interactions with its neighboring Galilean moons. As Io orbits Jupiter, these tidal forces flex its interior, generating heat that fuels its volcanic eruptions. This process, known as tidal heating, reshapes Io's surface in days or weeks, leading to constant geological activity. Europa is a moon of particular interest due to its icy surface, which conceals a vast, global ocean of liquid water beneath. This ocean could be in contact with a rocky seafloor, providing the necessary chemical ingredients for life. The potential for life on Europa is one of the most intriguing aspects of its study. Tidal heating, similar to that on Io, might keep this ocean in a liquid state. Recent studies suggest that plumes of water vapor occasionally erupt through cracks in the ice, releasing material from the subsurface ocean into space. NASA's upcoming Europa Clipper mission aims to conduct detailed flybys of Europa, gathering high-resolution images and data to investigate the moon's ice shell, surface composition, and subsurface ocean. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. What makes Ganymede particularly fascinating is that it possesses its own magnetic field, the only moon known to have one. This magnetic field likely originates from a liquid iron or iron sulfide core, similar to how Earth's magnetic field is generated. Ganymede's surface features a combination of older, heavily cratered regions and younger, grooved terrain, suggesting a history of tectonic activity. Callisto, the outermost of the Galilean moons, has the oldest and most heavily cratered surface in the solar system. Its surface has remained relatively unchanged for billions of years, providing a glimpse into the early history of the solar system. Unlike the other Galilean moons, Callisto shows little evidence of geological activity, leading scientists to view it as a largely dead world. However, recent data suggest that Callisto might have a subsurface ocean, though it is much deeper and less accessible than Europa's. Jupiter's massive size and gravitational influence have played a crucial role in shaping the solar system as we know it today. In the early stages of the solar system's formation, Jupiter's gravity acted as a cosmic vacuum cleaner, clearing debris from the inner solar system and protecting the terrestrial planets from frequent and potentially catastrophic impacts. By redirecting or capturing many comets and asteroids, Jupiter likely shielded Earth and its neighboring planets from numerous collisions. However, Jupiter's influence has not always been purely beneficial. Some theories suggest that Jupiter may have ejected a significant number of rocky planetesimals from the inner solar system, potentially preventing the formation of another terrestrial planet. Additionally, Jupiter's migration in its early history, when it may have moved closer to the Sun before settling into its current orbit, could have dramatically reshaped the solar system's architecture. This migration might have influenced the orbits of other planets and the distribution of smaller bodies like asteroids and comets. Launched in 2011, NASA's Juno mission has provided unprecedented insights into Jupiter's atmosphere, magnetic field, and internal structure. Unlike previous missions that only conducted flybys, Juno orbits Jupiter in a highly elliptical path, allowing it to study the gas giant up close. Juno's instruments are designed to peer beneath Jupiter's thick clouds, measuring the composition of the atmosphere, the depth of its cloud layers, and the nature of its magnetic and gravitational fields. One of Juno's significant discoveries is the observation that Jupiter's core might not be a solid object as previously thought. Instead, the core could be a diffuse region where heavy elements are mixed with lighter hydrogen and helium. This finding challenges previous models of gas giant formation and evolution, suggesting that the core might be partially dissolved into the surrounding layers. Juno's data also reveal complex atmospheric dynamics, including the structure of Jupiter's polar cyclones and the behavior of its jet streams, contributing to a more comprehensive understanding of the planet's weather systems. Jupiter continues to be a focal point of scientific investigation, with future missions poised to explore its many mysteries. NASA's Europa Clipper mission, scheduled for launch in the 2020s, will focus on Europa, one of Jupiter's most intriguing moons. This mission will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, aiming to assess its habitability and potential for life. Similarly, the European Space Agency's Jupiter Icy Moons Explorer, JUICE, mission, also set to launch in the 2020s, will study Ganymede, Callisto, and Europa, providing a comprehensive view of Jupiter's icy moons. These upcoming missions will build on the groundwork laid by Juno and other spacecraft, offering new insights into Jupiter's atmospheric dynamics, its magnetic field, and the potential for life on its moons. As we continue to explore this majestic giant, Jupiter remains a symbol of cosmic wonder and a key to understanding the broader workings of our solar system. From its immense magnetic field to its active moons, Jupiter stands as a testament to the complexity and beauty of the universe, inviting us to unravel its secrets and explore the far reaches of our cosmic neighborhood. This extended script provides a deep dive into Jupiter, its characteristics, and its role in the solar system. Feel free to adjust any sections or expand on specific details as needed.